and for our final talk of the TPDP 2023, we have Hal, who's going to be talking about publishing Wikipedia usage data with strong privacy guarantees. Thanks, Hal.
Hi, everyone. My name is Hal, and I'm a senior privacy engineer at the Wikimedia Foundation. Today, I'm going to be talking about some work that we did along with partners at Tumult Labs. And basically, I'm going to be telling you a story about how we published some Wikipedia usage data with strong enough privacy guarantees, hopefully taking you through some lessons that we learned, some problems that we encountered. Really just trying to give you a sense of the narrative of a real life DP deployment. So here's the table of contents, hopefully give you a little context on the problem, take you through the build stage, the tuning stage, and the deployment stage, and then talk about some lessons that we learned along the way. So let's get into it. So I work for the Wikimedia Foundation. We're best known for Wikipedia, which I'm sure all of you use. I do myself. But we also release a ton of other projects ranging from Wikidata, MediaWiki, Wikimedia Commons. And cumulatively, we get around 22 billion views to our project every single month. These projects span 803 separate instances of the MediaWiki open source software. I think now we're at somewhere like 330 languages that we cover. And it makes us like 6th or 7th largest website. So we have a lot of useful data about the internet. And one of the key policies that governs how we use this data is our open access policy. And this is just a screenshot of the Wikipedia page where this policy is written. Basically, what this says is we want to make as much data as possible open to researchers, to community members, so that they can understand what's happening on the internet, make decisions about what's happening on the wikis, etc. Now, this takes a couple different forms. For example, the revision history of every single Wikipedia page is public, as you may know. So you can go through, and this is for differential privacy. But it also looks like a couple other things. For example, we release page views that are split up by country, and also page views that are split up by project. Now, on the other side of the coin, we have the lean data diet, which is an internal term. And this is defined by our privacy policy and data retention guidelines. And this basically lays out 3 fundamental principles. Firstly, we don't have any first-party tracking cookies that tracks people across sessions or even within sessions, right? So if user A comes to our website on day 1, and then they come back on day 2 from a different IP address, we won't know necessarily that it's the same person. Secondly, there's no account that's needed to read or to edit Wikipedia, and this is a fundamental aspect of how the site works. And then finally, we have a pretty aggressive data retention policy, which says that any personally identifiable information, namely IP addresses, user agents, etc., those are going to be aggregated and deleted after 90 days. So in 2020, community members online requested that we release page views by both country and project. I mentioned before that we release it by country and project separately. They wanted the intersection of those 2 data sets. This would be known as the page view data release. That's how I'm going to be referring to it for the rest of this talk. And this data release illuminates a tension that we have between privacy on one side and transparency on the other, characterized by these 3 policies. And the stakes are high here because Wikipedia is an inherently political project. Oftentimes, users and editors might be editing sensitive information, sensitive pages, medical information, political stuff, and they're pseudonymous for a very good reason. And because of there's this tension, differential privacy could be useful. That was our hypothesis for this whole project. So let's talk about the release. We worked with Tumult Labs, and we specifically used their Tumult analytics software. I've been using it for a couple of years. We chose Tumult specifically because they're open source, like many of the DP software projects that exist, but also they integrate really well from a parallelism Spark perspective, and that just played well with our internal servers. So they have this approach, which splits things up into 3 stages: build stage, tune stage, and deploy stage. And we're going to go through each one of these bubbles piece by piece and talk about how this process worked for the Wikimedia Foundation. So let's define the problem and some success metrics. Broadly speaking, the problem we're trying to solve is that we want to release as much data as possible about reading activity. We want to partition it by project and page, and we want to release it every single day. And as far as success, broadly speaking, we're going to get into more specifics later. It looks like we want privacy to be protected at a user day level. We want the data to be better than a baseline, right? More plentiful and more granular. And importantly, we want the output to be equitable, and trustworthy for consumers. When people are downloading this data and using it for their analyses, we don't want them to be confused or have any issues with equity. So this is attempt 0, first attempt at implementing a prototype. For all of these diagrams, we're going to be coming back to several of these. Red is sensitive or private data, and green is public or non-sensitive data. So we're going to follow basically standard protocol here. We're going to try and limit the maximum contribution per user. We're going to enumerate a list of all of the possible page country tuples. We're going to do a private group by and count, computing the exact counts. And this is where it breaks down for attempt 0. And what's the reason? We have 60 million pages and we have 214 countries. If you do a cross product of those two things to get the whole key set of every single possible page country tuple, it's around 12.8 billion possible combinations. And we just don't have enough compute for a key set of that size. We could do it eventually, but it would make everybody who's also using the cluster really mad because we'd use 100% of the Spark cluster for multiple days. And we just don't want to do that. So what's a lesson here? Doing DP with big data means that technical constraints are actually existential to the success of a project. If you can't work around these technical constraints or within them, you're going to have some issues. So let's go back, start where we left off, and let's take advantage of some public data. So we already publish some global page views, sort of like a YouTube view counter for pages on a day-by-day basis. So we can use that data to limit the number of pages that we're considering. And if we limit to just the pages that received more than 150 views globally, rather than country by country, it reduces our total number of pages to around 500, 600,000, and our key set size is around 120 million page country tuples, which is much more tractable. So continue with our pipeline. We add some DP noise at the counts, and you can see it goes from red to green to indicate that the data is now safe. We remove low counts, and we're going to get more into this step later on for accuracy, equity, et cetera. And then finally, we publish the data. So this works, and we're using what I think of as probably like a standard DP software pipeline implementation. Epsilon is 1. We're using Laplace noise, pure DP. Our noise scale is 10, so we're considering 10 page views per user. And we're defining a user as the hash of an IP address and a user agent, so we don't collect any cookies. So how does this do? Is the data more plentiful and granular? Yes, that meets that success metric. But is the output equitable, accurate, and trustworthy for consumers? Turns out no, it depends on which metrics you're looking at. So let's look at these metrics that we're considering. First, we're shooting for a median relative error of under 6%. And median relative error is just if you compare the true distribution and the noisy distribution, and you look at the median of that, what is the relative error there? And then secondly, we're looking at something that I call drop rate, which is, I think of it as similar almost to like a false negative rate. It's the percentage of above threshold values in the true distribution that have negative noise added to them and then fall below our threshold and are not published. So it's like data that should have been published in a perfect world, but was inadvertently dropped. And then conversely, we have something that we call the spurious rate, which is the exact opposite, slightly more intense, where what percentage of zero values, because this data is very sparse, get so much positive noise added to them that they're above the threshold and are sort of inadvertently published when they shouldn't be. And why are drop rate and spurious rate important? As I said, data is sparse and has a really, really long tail. So if we're adding a bunch of noise to this distribution, there's going to be some times where we're adding 4 standard deviations, 6, 7, 8 standard deviations away from the normal value in the middle. And meeting goals in equity, accuracy, and trust require actually optimizing for all of these metrics, not just median relative error. And I'll get into what that looks like. So we have our global metrics here, and our goal values were less than 6% and less than 1% and less than 1%. We're meeting all of these on a global level, but what if you look at subglobal metrics? This is what we call the Micronesia problem because it popped up most impressively, I guess, in Micronesia. Micronesia is a small subcontinental region, contains 7 Pacific Island nations, and it has very little traffic to our services. So in our naive first implementation with the initial parameters that we set up, more than 99% of the published data from this subcontinental region was spurious. We were releasing 225 pages, and only one of them was actually true data that should have been released. And when this also generalizes, so 9 out of 23 subcontinental regions had more than a quarter of the data was spurious. And this was concentrated in places that we were trying to focus on equity and accuracy. So Africa, Oceania, Central Asia, and the Caribbean wanted to make sure that we were doing right by the places. So the lesson here is that global metrics can actually conceal local equities. And also that sparse data and large key sets mean that long tails are actually a threat to equity, accuracy, and trust. So we'll go back and try this again, attempt 2. And what we'll do is, instead of using a standard Laplace mechanism, we'll try using a Gaussian mechanism. And why are we doing that? The pros here are that the tails decay significantly more quickly, which means that the spurious data goes down and the median relative error goes down, particularly in these low traffic regions. We also can take advantage of looking at unique page views, which I'll talk about in a sec, to lower the noise scale to the root of k rather than just the normal sensitivity. Cons is that the overall median relative error goes up because the middle of the distribution is a little fatter. So globally, we do a little worse, but locally, we do significantly better. Now, how does this do when we change our distribution? Data is more plentiful and granular than the baseline, as we said before. And yes, this actually meets our output equity, accuracy, and trust levels that we want. The spurious rate goes down to around or less than 1%, both globally and for almost all of the subcontinental regions. Now, does this protect privacy at a user day level? Not so much. And we'll talk about the hash of IP address and user agent, which has a bunch of known failure modes. So we wanted to bound our user contributions. We don't have any first-party tracking cookies to do that. We can look at the hash of the IP address and user agent, but that fails in a bunch of contexts. Specifically, imagine you're browsing on mobile on a cell tower and you switch IP addresses because you change cell towers. All of a sudden, you appear as a different person on our system, which is great. Or you're connected to the B Wi-Fi and you're on Safari on your Apple device, and every single is the exact same user agent, exact same IP, you're artificially aggregated together. A bunch of failure modes there. So instead, what we did is something called client-side filtering. And I can get much more into this, but the crux of this is that with every single page view, your browser will send a Boolean value, either a 1 or a 0, on some client-side logic that says either include this in the aggregation or do this in the aggregation. And we can convert this to just being unique page views, which is great. As I said, if we do unique page views, we can add significantly less noise. And this was also great for Tumult Lab, specifically because it required a novel definition of neighboring data sets, and Tumult Analytics was capable of supporting that novel definition. So there are more specifics in an appendix. I can show you some more like pseudocode stuff further on. So lesson here is that data minimization and strong DP actually can strong DP guarantees can actually be in conflict with each other. If we're not collecting enough data to identify a user, hard to guarantee user level privacy. So attempt 3, we limit the contributions using client-side cookies rather than the hash of IP address and user agent. And we have our parameter table here. And how do we do? We're meeting all of these things that we're trying to reach on a broad level. And then from an output quality perspective, we also are meeting our equity, accuracy, and trustworthiness goals. We're hitting these numbers. And then also significantly improving on a baseline non-DP data release. Namely, we're able to 4x amount of data that we release on a daily basis, which is really great, and include more than 2.5 times the amount of underlying data compared to a non-DP data release, which was looking at similar outputs. So as we go to the final stage, the deploy stage, we find the algorithm by wrapping it up in a Python package, deploying it using Airflow so it can get orchestrated on a daily basis without someone having to click the button. We write some documentation, both slightly more formal for people to look at the privacy guarantees. This is also public, and slightly more less formal for data consumers so that they can understand exactly what it is they're getting. Also, if you want to go back and take a photo of that, go ahead. Great. And then finally, we deploy it, and it doesn't look like much. It's just a list of TSVs right now, but each one of these TSVs contains around 360,000 rows of data. If you want to download it, here's a link shortened link. It'll take you right to the page. The documentation is right at the top, 00 readme.html. And finally, we get some interesting outcomes, right? We can look at languages that are spoken in more than one country. Oftentimes, there are huge spikes in page views that happen when a celebrity dies. Sometimes it can even take the site down, which is not great. But you can actually look and see in different countries how different traffic was being routed. This is a log scale, so there's a significant difference between Chile and Spain, for example. And then also you can look at countries that speak more than one language. So this is the number of views that the Morocco earthquake from a couple weeks ago was getting in Morocco in both Arabic and French. You can look at the distribution within a country of how information is being consumed. Yeah, okay, so this is a summary slide, basically summarizing challenges, solutions, lessons learned throughout this whole process. And the bottom line is this: practical concerns for large-scale DP deployments are really different from theoretical concerns. And I'm not going to go through every single one of these, but we can come back to this if necessary. Yeah, thank you so much. Any questions? Also, feel free to send either Tumult or me an email if you have any further discussion you want to do.
For a question or two. We have one from Slack. Says, after client-side filtering, it was relative error compared with noise plus client-side filtering and no noise and no client.
Okay, so if I'm understanding the question correctly, it's saying, how does the error introduced from filtering on client-side filtering compare prior to and after implementing that as a solution? Yes, it's actually pretty comparable. It was, yeah, relatively comparable both before and after. Interestingly enough, if you go and you look at the hash of IP address and user agent versus client-side cookies, you end up seeing that like globally, a lot of the metrics are relatively stable. Turns out that IP address and user agent, even though it has a bunch of known failure modes, on a high level is relatively performant. And it's hard to really disambiguate between before we implemented this and after we implemented this.
Good question.
Yeah.
You touched on the fact that data minimization and your DP, like DP, were kind of the thing you did for data minimization actually hurt your privacy.
Yes.
And you introduced cookies back in as a result to get the
yes. Yeah.
What do you, I guess, think in general, like, do you think there are system solutions required there to kind of make sure that those cookies can't be things you originally didn't want?
Yeah. Yes. Basically, the cookies is complex. As far as the security model that we are operating under, WMF as an organization, we only get a binary flag with each page view, right? So like, you know, it's IP address, user agent, what page they visited, some other metadata, and then like include DP, yes, no. Which means that the amount of information that we receive is actually quite minimal. It's only one bit extra. And from a security perspective, our assumption is, you know, we're not receiving this. If someone has access to a user's browser, they could potentially see like the hashes of the pages that they visited in a day, but also then they would have access to their browser and could just go into their history anyway. So it feels like a kind of negligible security privacy loss there. More generally, I think that the tension is true. Like if you minimize data to the point where you can no longer adequately identify a user, it's hard to protect that construct if you don't have the construct internally in your data set. And you can work around it. Really, this is not user level privacy, it's browser level privacy if people aren't clearing their cookies between every single request, which is, you know, a slightly different construct in reality, but we call it user level privacy because it's easier that way. Yeah.
So you found user contributions 10 per day. How did you choose that?
That was experimentally derived. We, you know, but between this initial prototype and the doing a subglobal analysis, we ran like 700 experiments to figure out which hyperparameter set made the most sense, and narrowed it down to a few, and then dug into, you know, specifically, you know, if we're looking at subglobal metrics, how do these all perform, and then picked one out of those.
Okay, one more question.
Yeah, similar, but how did you choose that spot? Like decided organic world experiments? How do you guys come up with the
Oh, I mean, it's a round number. I don't know. It was experiment. Also, it was a parameter that varied in our experiments, and we had like I had a feeling that I didn't want to go over 1.5 or 2, but ultimately, you know, as it's similar almost to like a what's the optimal threshold for a given context in ML algorithm, right? Like someone decides and it's a number, and like, you know, you try to give the full context, but also it's just like it's a parameter that you set. So yeah, I mean, like, didn't want to go over 1.5 or 2. 1 did well enough. 0.5 added too much error. So why not? Yeah.